Welcome back to The Explainer. Today, we're going to pull back the curtain on the secret language of computers. And you'll see, step by step, how these really simple, basic ideas stack up to create some mind-blowing complexity. So, think about this for a second. There's this massive communication gap, right? Between us and all our gadgets. I mean, we experience the world in, full color, full sound, all this amazing detail. A computer? It's basically just looking at a bunch of on and off switches. So the big question is, how on earth do you bridge that gap? Well, if we're going to translate our world into its world, we've got to start at the very beginning. I mean, the absolute most basic, smallest piece of information a computer can even wrap its head around. And here it is, the bit. Seriously, every single thing you do on a computer, sending an email, playing a game, yeah, even watching me right now, it all boils down to this one simple concept. Two states. That's it. On or off, 1 or 0, high voltage, low voltage. It sounds almost too simple, right? But trust me, this is the bedrock for literally everything else. Okay, so a single bit by itself isn't super useful, It's like trying to write a novel with only the letter A. It's just not going to work. To say anything meaningful, computers have to start grouping these bits together, kind of like forming letters into words to build a real alphabet. And that brings us to the byte, a group of 8 bits. Now, the key word to latch onto here is addressable. What that means is that a byte is the smallest chunk of data your computer can actually pinpoint and grab from its memory. Think of it like this. Every single byte has its own unique street address. It's how the computer keeps everything organized. All right, so we go from bits to bytes, and from bytes, we level up to something called a word. Now, a word isn't just a random collection of bytes. It's super important because it's the natural chunk of data a computer's processor is built to handle all at once. So when you hear 64-bit computer, that means its brain can process a 64-bit word in one single operation. It's like taking a huge bite of an apple instead of a tiny nibble. That's why it's so much faster than, say, an old 16-bit machine. So check this out. This lays it all out pretty clearly. You can see the whole pyramid here. We start with that single, lonely bit. Then a group of 4 is called a nibble. Yep, a nibble. 2 of those nibbles make up our byte. And then you group those bytes together to form a word. See how it works? Each layer just builds on the one before it, creating this really organized, structured way to manage all this information. Okay, so we've got our alphabet down, bits, bytes, words. Check. So now let's see how a computer uses this new language to do something super basic, something we all learn as kids, counting. But get ready, because they do it in a way that's totally different from how we do. See, we humans are all about base 10. It makes sense, right? We have 10 fingers, so we use 10 digits, 0 through 9. Each spot in a number, the ones place, the tens place, the hundreds place, is all a power of 10. But computers? They only have 2 fingers, on and off. So they're stuck with base 2. They only have 2 digits, 0 and 1. And for them, each spot in a number is a power of 2. It's the exact same idea, the same logic, just with a much smaller set of tools. And this is where it gets really cool, because we can actually translate any number from our system into theirs. It's like cracking a code. So let's try it. We're going to take the number 625 and translate it step by step. Okay, the method's actually pretty straightforward. You just ask yourself, what's the biggest power of 2 that can fit into my number? For 625, that's 512. So you subtract it, and you put a 1 in the 512's place. Now you've got a remainder, right? You just do the exact same thing again. What's the biggest power of 2 that fits into that? And you just keep going down the line. Every time you use a power of 2, you put down a 1. For all the powers you skip, you put down a 0. And boom. Just like that, our 625 is now 10011100001 in binary. All right, so positive numbers, nailed it. But hold on, what about negative numbers? I mean, how does a simple system of on or off possibly represent something that's less than 0? This was a really tricky problem for early computer scientists to solve. And the solution they came up with was actually pretty clever. They decided to just sacrifice one of the bits. The very first bit in a number, the one all the way on the left, it doesn't count towards the value anymore. Instead, it becomes a signpost. If that bit is a 0, the number's positive. If it's a 1, the number's negative. Simple as that. Now, the first couple of tries at this, things like signed magnitude and ones complement, they made sense on paper. But they both ran into the same really weird critical flaw. Get this, they both ended up with two different ways to represent the number 0, a positive 0 and a negative 0. And for a computer, which needs things to be perfectly logical and efficient, having two ways to say nothing is a huge headache. It's just messy and wastes valuable space.
So that mess led everyone to embrace a much more elegant solution. It's called 2's complement, and it is the standard that pretty much every modern computer uses today. And for good reason. It completely fixes that 2 zeros problem, and as a really nice bonus, it actually makes the physical circuits that do the math inside the chip way, way simpler.
So how does it work? It's a neat little trick. You want to make a number negative? Okay. First, you take its positive binary version. Then you flip every single bit. All the zeros become ones, all the ones become zeros. And for the final step, you just add 1 to the result. That's it. This whole flip and add 1 thing gives us a super reliable and efficient way to deal with negative numbers. Okay, so we've got a handle on whole numbers now, positive and negative. That's a huge step. But let's be real, if that's all computers could do, they wouldn't be very useful, would they? The real world is messy, so it's time to tackle the final and maybe most important piece of this puzzle. Which brings us to the next obvious question, right? What about all the other numbers? You know, numbers with fractions or decimals, like pi, 3.14159, or even just the price of something, like $2.50. The world is full of these numbers, and this system we've built so far, it has absolutely no way to represent them. The solution is this really brilliant idea called floating point representation. And here's the cool part. If you remember doing scientific notation back in science class, you've already got the basic concept down. It's all about separating a number into two parts, the actual digits, and then a separate instruction that says where the decimal point is supposed to go. So, a floating point number gets broken into 3 little pieces. First, you've still got that sign bit. Is it positive or negative? Easy. Next, you have a part called the mantissa. That's just a fancy word for the significant digits of the number. And then the third part is the exponent, and its only job is to tell the computer how far to shift the decimal point, either left or right. By combining these 3 little chunks of information, you can represent a massive range of numbers, from teeny tiny fractions to gigantic astronomical figures. So let's just take a step back and look at the big picture here. Isn't it kind of wild? We started with a simple on or off switch, a single bit. And just by layering one clever rule on top of another, we built this incredibly sophisticated system that can represent pretty much any number you can throw at it. But when you peel back all those layers, what's at the very bottom? It's still just patterns of ones and zeros. That's all it is. And you know, this binary system has been the absolute backbone of computing for decades, for more than half a century. But now, as we're diving headfirst into this new world of AI, and, even quantum computing, you really have to start asking the question, how much longer will this simple language of ones and zeros be enough? Will it hold up? And that's the thought we'll leave you with today, here on The Explainer.